Hello everyone. This video will be going through the magic number challenge on Ethernaut. So this challenge requires us to write some bytecode that returns the number 42 when what is the meaning of life is called on our contract. And so we must write our contract in 10 opcodes at most. And so the way we're going to solve this challenge is we're going to first create a normal contract in Solidity that returns the number 42, and we'll see what kind of bytecode that produces, and we'll analyze it and see if we can make our bytecode with 10 opcodes at most. So this diagram here demonstrates the contract creation flow. And so once we create a contract, that contract is sent to the Ethereum network, and then the EVM compiles the contract into bytecode. And this bytecode actually contains two separate parts. The first part being the contract initialization instructions, and then the second part being the contract execution logic. And so this contract initialization instructions might include things in the constructor, among other things. And then, so this is the part that's only run once when the contract is first being deployed. And then the contract execution logic down here will be returned to the EVM after the contract initialization instructions are run. And that is actually what's stored on the Ethereum network and gets run every time you call a contract. You can find this diagram on this Medium post here by OXSage. It's right here, and a link to this walkthrough will be in the description below. So now let's go over to Remix to create our Solidity contract. So I've written a few things here already, most notably this attack contract right here. And so this attack contract, all it's doing is when this function, what is the meaning of life, is called, it's returning a uint256 value 42. So if we compile this and deploy it, should be the attack contract here. You can see that contract has mined. And so what is the meaning of life here? That should return 42, but I won't run that right now. That's okay. What I'm going to do instead is I'm going to go to this block here where it was mined and click on debug and start debugging. On the left hand side here on the debugger window, we should see a list of the opcodes that are run when this contract was first deployed. And so when, the first instruction we see is push 180, and then we see push 140. So if we look at the EVM opcodes reference here, that push 1 so this push 1 operation is taking is putting the value that we pass it onto the stack, onto the very top of the stack. So it's pushing the value 80 and then 40 onto the stack here, and it's calling this mstore function here. So going back to our opcode reference, we see that this mstore function takes the first element on the stack as the offset and the second one as the value, and then what this does is it stores in memory the value at location offset to offset plus 32. So what our code was doing back here was it was putting the value So if you have a look at the stack, it's pushing the value 80 onto memory location 40. So that's what that does. And then this is this call value function here. Is getting message.value, which is basically the how much way was sent to the contract when that contract was called, which in our case was 0. So when this call value function is run, we should see 0 onto the stack, which we do. And then dup1 is pushing the value that was on the stack again onto the stack, so it's duplicating the value. Since we have 0 on the stack, duplicating that, we should just have another 0 on the stack, and then we run this is0 function, which takes away the top element on the stack, and then replaces it with either a 1 or 0, 1 for true, 0 for false, on whether that value was 0 or not. So since we do have 0 on the top of the stack right now, this is0 function should produce a 1 on the top of the stack. And then what we're doing is we're pushing, we've got push 2 now instead of push 1, which means we're pushing 2 bytes onto the stack, 0, 0, 1, 0. And then we're jumping to that location with a if condition here. So if we look at jump I, we can see the destination is the top of the stack. The condition 1 or 0 is the second one on the stack, and we're jumping to our destination memory address if this condition is 1. And if we remember, we have a 1 for the condition because we the value of that is 0 was true, so we've got a 1, and then we're going to memory address 10, so we're jumping to that location here. So what that part was doing is making sure that there was no value attached to our function call, and if there was any way attached to our call, it would just skip this jump I and it would revert right here. But since we had 0 value, we're going to this jump dest location, and then we're popping the first element off the stack. So we've gone to jump dest, and then we pop that element off the stack. So now we've got nothing in the stack, and then we're pushing the value b6 onto the stack, and then duplicating that. We've got 2b6, and then we're pushing 2 bytes again, 001f, so that should just be a 1f on the top of the stack, and then we're pushing 00 onto the stack, and then we're running this function code copy. So this code copy, what that does is it takes a destination offset on the top of the stack, second element on the stack is offset, third element is the length, and we're putting into our memory at location dest offset to dest offset plus length, so dest offset and length. We're putting the code that is at the location offset, which is in the middle. So if we look back at our Remix IDE, on the stack, we've got 00 on top of at the top of the stack. 00, so that's the data offset in memory. So in memory address 0 up to memory address, the third element is b6, up to memory address b6, we're going to be putting the code of of b6 length from location 1f in our code here. So if we convert 1F from hexadecimal to decimal, that's 31. So if we go to line 31, we're copying code from here, 31 all the way up to a length of B6, which is 182 lines. We're copying 182 lines, so we're actually copying more than there is code here, but that's okay because all of them will just be replaced with zeros. So we're copying all of this code and then putting it into our memory at location 0 with this code copy function right here. And you might have guessed, so this is the constructor part that we've been running here, and this code is actually the runtime code that we've been just talking about before. So this is the code that's actually going to be stored on the blockchain and run when we call our contract. So we copied that code onto into the memory address location 0, and then we're pushing 0, and then we're returning. So that was the end of the constructor here. So to be able to create our own contract, we will need this constructor code here. So we will take all of that. It was up to line 30. I'm going to go back to the beginning, up to line 30 here. And I'm going to copy all of this here, and I'm going to paste it. And so this is our constructor here, but we're going to need to change a few things here so that it will fit with our code that we run. For example, this B6 value here. So we don't want to be copying B6. We're going to be copying at most 10 opcodes, right? And so 10 opcodes should be length 0A, which is 0A is just simply 10 in hexadecimal. So that's the first change that we can make to our constructor code here. And so now we need to create code to return 42. And so we can just start creating that just down the bottom here. So to be able to do that, what we'll need to do is to push some values onto the stack first. So we'll be pushing the value we're going to be pushing 42. And so if we go back to our hexadecimal here, so 42 in decimal should be 2A in hex. So we want to push our value 42 onto the stack. We need to push that value into memory to be able to return it. So we're going to be pushing that value 2A at memory location 40. And then we want to just store that in memory. And so when that's done, what we'll do is, so we need to be able to return this value right here. So if we go back to our EVM reference list, we see this function return here. And what return does is it returns the contract call with the value at memory at location offset and offset plus length. So we need to push two values onto the stack. So we're going to need to push length first, and the length of our value here, 2A, and so 32 in hex is just 20. So we're going to need to push 20 onto the stack. And so once we've pushed that, we'll need to get our offset. And if you remember, our offset we set as 40, so we're going to push 40 onto the stack, and then we want to call this return function here. Okay, and so this should be our opcode to be able to deploy our contract first, and then our function is right here. And if we count the number of opcodes, it's 1. So this push function actually takes 2. So this push 1, if we go back here, so this push function has code 60 here, and then it takes in a value. So that's actually 2 opcodes running there. So there's 60 and then the value that we're going to push on there. So that actually counts as 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got exactly 10 opcodes in our contract. So that's a good sign. So what I'm going to first do is I'm just going to copy the bytecode for this opcode here from our Remix IDE. So this right here is the bytecode that represents all of this opcode. So I'm going to copy that. I'm just going to paste that here. Just clean it up a little bit. Okay, and so we can start to just make sure that this is correct by looking at, so push 1 had code, if we go back to this here, 60. So we've got 60 at the beginning, and then we've got 80. So we're pushing 80, which seems like it corresponds to this first line. And then we're going to be pushing, so 6040, which corresponds to this second line, and then mstore. So if this bytecode is correct, 52 should correspond to mstore. And it indeed does correspond to that. So this bytecode looks to be correct. So I'm going to find where we return in this code. So return corresponds to F3, which we find right here. And then we're calling one more opcode invalid, FE. So if we go back here, FE shouldn't correspond to anything. So yeah, FE is invalid. So this is the end of our constructor code here. And so this is the bytecode that we're going to change. So we can delete all of this here. The bytecode corresponding to our payload contract here. So if you remember, push was 60, and then we're pushing 2A, and then we're calling the push 1 function again, so 60, and then we're pushing 40 onto the stack, and then mstore, if you remember, was 52. And we're pushing again, so 6020, we're pushing 60, and we're pushing 40. And then we're calling return, which was F3. So this should be our bytecode for our payload. So I'm going to just copy that and paste it on the end of our bytecode here. So if you remember, we changed this value here, the push 1, I think it used to be B5, I believe, B6, and we changed this to 0A. Yep, so it's right here. It used to be B6, but we want to change it to 0A so that we're not copying B6 amount of code, but we want to just be copying 10 opcodes. So I'm just going to write 0A instead of B6 here. To be able to deploy this bytecode onto the blockchain, what I'm going to be using is this contract called deploy bytecode. And so I actually got this the code for this contract from this GitHub repository right here, and just slightly modified it so that I can easily see the address where that contract was created easily on the Remix IDE. And I also just put in these two brackets here, call data size and then bracket, just so that I can compile in Solidity version 0.8.0 or greater, just because this one is using an outdated Ethereum version. So I'm going to copy this and just deploy that bytecode. And so our address is this value right here. So I'm just going to double check that again. So I'm going to go to Etherscan and click on contracts, and there we see we've only got 10 opcodes worth of bytecode here. So this seems good. And so what I'm going to do now is I am going to go back to Ethernaut and just submit that address. So await contract dot set solver, and that's going to be our new address here. And so now our new solver address should be our new address here, which indeed it is. And so now I'm going to just go ahead and submit that instance. And there we have it. So we have successfully completed this challenge.